Regular expression is available in many programming languages. In this video, we will see regular expressions in Julia programming, how to write and match regular expressions in Julia programming environment. I am using Julia extension in Visual Studio Code to write and run Julia code here. Regular expression syntax in Julia is based on PCRE library, compatible to Perl programming language, but many of the things are very much Julia programming specific here. This is a text file with the name search_file. I can import text from this file here in Julia. Copy this path, then come back here to write cd within parentheses using raw prefix within double quotes. Paste the path, run this line to fix that folder as working directory. Then call this read function, pass the file name search_file.txt, comma. We want to import the text file as a string object. Assign it to a variable str. Run this line. All the information from this file are imported here as a string object str, and it shows existing text inside the file in this raw format here in repo. And if we print str, run this line, it prints text from the file formatted line by line in a proper readable way. It contains information in which we will search for specific patterns. Before we try to do that, let me split this editor and I can bring this search file here in this side so that we can view this text file. In Julia, we can use indexing to get specific characters from this string str. This is the fourth character, A here. These are the characters located at the position indices through 5 to 70 in the string. You can notice together with these usual characters, these escape sequences, carriage return and new line characters here, which exist just before every new line here in this text, and those are visible in the raw format only. These are 9th, 1st and 16th character, together E, capital A, space. If we pass a character to find first function, as example character T, pass this string object str fetched from the search file, run this line, it provides the position index of the first character T in the text right here. If we pass character T to find last function, pass this string str, run this line, it provides the position index of the last character T in the text below here. Similarly, if we pass this escape sequence for tab character, run these two lines, it provides respective first and last position indices of the tab character. If we pass this predicate is equal tab character to find all function, pass this string object str, run this line, it gives all the position indices of tab character in the text. Instead of is equal, we can simply write this comparison operator also, as all operators in Julia can be used as functions. Find next function can give us the position index of this character after a specific index. Run this line. Find pref function can give us the position index of this character before a specific index. Run this line. Instead of a character, we can look for a piece of string also. As example, if we pass this string on to all these functions, run all these lines. Instead of indices, we get respective ranges of indices in which this string pattern on exists in the string str from the search file. And here, if we pass this string to find all function, run this line, we get all these ranges of indices in which this pattern exists. These are some inbuilt Julia functions using which we can get to know about existence of any string or character pattern in the search file. Let me take another pattern string f capital S E, assign it to a variable pattern, run this line. Type of pattern is string. This pattern exists in string str. False. Let's do little change. Provide a space in here in this pattern. Run this line. Now this pattern exists in string str in range 177 to 180 right here in search file. This pattern is taken here as a string object. Instead of taking it as a string literal, if we take it as a regular expression or regex object, run this line. It becomes a powerful tool and we can manipulate it in so many ways that it can help us to get most relevant information from a text file we import as string here to search in it. To construct a regex object, we can simply prefix r to this double quoted string also. Run this line. Type of this pattern is regex now. This pattern exists in string str true, and this pattern exists in the same range 177 to 180. Occursion function can inform us only whether this pattern exists in the string by providing boolean values true or false. To get to know how the pattern matched for the first time in the string, we can use match function. Pass this pattern, pass string str, assign it to a variable m, run this line. It provides this regex match object showing this matched pattern in search file. M, this regex match object, has this regex field. Run this line. It shows the regular expression or regex object this regex match object M matched for. M has this upside field. Run this line. It gives the index at which the match took place. Pass this regex match M and this offset to println function. Then open Julia repo. Run this whole Julia script. It prints the regex match object and the position index at which first match took place in the string str imported from the search file. Remove this space from here. Change this regex pattern to F capital S E. Now run the script. It gives nothing, which does not have any offset field obviously. Wrap this pattern within square brackets. Then run it. Now regex engine in Julia looks for this character class, either F or capital S or E in the string str. In this case, it matches E because among F, capital S and E comes first right here at position index 7. If we pass a caret here, it will negate this character class and will look for the characters which is neither F nor capital S nor E. Run it. It matched capital A at position index 1 because it is the first character in the search file that is in string str, which is neither F nor capital S nor E. Regex objects or regular expressions are composed of two types of characters, metacharacters and normal literal characters. Through metacharacters, we command or control the way we want to match a pattern in a string. As example, here these special characters, square brackets, and this caret are metacharacters, and these are literal characters. A list of metacharacters you can find within the links I have given in description below. I can open this list here also. If we pass a literal character D here, run it. It provides the first match to character D and its location index, it is here. And if we pass this \d here, run it. It matches first digit in the string. As you can see in this list, this is a metacharacter, matches any digit in 0 through 9. Equivalently, we can pass this character class 0 through 9 also. Run it. It provides the same match. \D matches character which is not a digit. That means \D negates this metacharacter \d. If we run it, it matches to the first character, which is not a digit here in search file. Obviously, it is capital A at position index 1. \w matches word character. Run it. It keeps the first match, capital A again. \W negates the metacharacter \w. If we run it, Julia matches the first non-word character in search file, this space here, at position index 13. \s matches a white space. It can be a space, a tab, a new line character, or a carriage return. Run it. It provides the same first space character. \S matches any character which is not white space, so it keeps the first character capital A. Dot is a metacharacter which matches any character except a new line character. Hence, if we run it, it matched the first character capital A. If we want Julia to match a literal dot, we need to escape it using \. Run it. It matched the first dot here in search file. If we want it to match this $11.3 here, we can write here 11 followed by literal dot followed by 3, and at front we need to escape this $sign because dollar is another metacharacter we will see later, and dollar is used to interpolate objects inside a string in Julia also. Run it. Here it is. To match a character which is either of many types we permit. As example, if we want Julia to match a digit or a non-word character or a literal capital S, we can use alternation using vertical slash this way. Run it. It matched this space because it is the earliest character among the characters we permit here. Of course, we can put all this within square brackets also to form a character class. Run it. We get the same match. We have seen usage of caret before to negate a character class within square brackets. If we simply pass caret, it works as an anchor to match beginning of a string. Whole text in the search file is imported here as a single string object str. Beginning of the string str is right here with capital A followed by R. So if we write here caret followed by capital A R, run it, it matched capital A R itself at first position index. Dollar is another anchor. It matches ending of the string. Text in the search file ends with L. So this regex pattern L followed by dollar, run it, it gives the match at the last position index in string str. If we take .html followed by dollar, run it, it gives this match. If we omit L from here, run it, it provides nothing because anchor dollar follows L, not M, at the end of the string str. \b is another anchor. It is called word boundary. It signifies start or end of a word in the search file. \b capital S, run it, it matches here since in this word some capital S is preceded by word boundary. \b, run it, it matches here since in this word E is followed by word boundary. If we take \b, run it, it matches nothing. But if we take \b, run it, it matches here. Since \y, then it has a word boundary here. \B negates the word boundary \b. It means not a word boundary. If we omit this y from here, run it, it found the earliest match here now, since this pattern RR is followed by not a word boundary here. So if we take word boundary followed by capital H, A followed by not a word boundary, run it, it matches here. And if we take word boundary followed by capital H, A followed by one more word boundary, run it, it matches nothing. We have seen already \w is a metacharacter. It matches any word character including letters, digits and underscore. So it matches the first word character uppercase A here. If we pass a plus here, run it, it matches this entire sequence of word characters from the beginning till this regex engine reaches this non-word character space here in first come, first served manner. Plus is a quantifier here. It matches one or more characters. Now in this regular expression, if we write colon just after this metacharacter \w, run it, it does not match anything from beginning. Rather, it matches here this word character k followed by colon. And if we pass this plus quantifier here to permit it to match at least one or more word characters up to a colon, run it, it matches all word characters from here till colon. At this point, it would be better if we get to know some of the things about internal mechanism of a regex engine. How does it work in backend in this case? In this regular expression, these are two sub-expressions or tokens. One is \w plus for matching one or more word characters, and another is this literal character colon. Regex engine in Julia is regex directed. That means it first checks each token in the regex in turn, act accordingly to find matches in the input string. Whenever required, it selects one token and remembers the other to return to later if necessary, until desired match is found. Let's remove this plus quantifier from here for now. If we run it, for this first token, regex engine attempts to match a word character at the beginning of the input string here. It matches capital A. Then it checks the next token in the regex, this literal character colon. Attempts to match the next character, but it cannot find the colon character here because it is R. That's why it backtracks into this token again in regex, attempts to match next word character. It finds R. So it fails to match a colon again for the next token, literal character colon in regex, because it is again R. This way regex engine keeps attempting till it fails to match a word character for the first token here, because it is a space, not a word character. Eventually it starts attempting to match at this word character T here for first token. It fails to match a colon for the next token again. It does not stop till it finds a word character for the first token and a colon for the second token here. Finally, we get this regex match k followed by colon when we run it. Now keep this plus quantifier here in regex for matching at least one or more word characters. So in this regex, for this first token here, regex engine matches word characters as many as possible from the beginning till it reaches this non-word character space here. Then it proceeds to this next token, literal character colon in regex, which fails to match as there is no colon character here. So it backtracks to the first token, remembers till which character it has already tried to match. It restarts matching from here. This way, finally, when engine restarts matching from here for first token, it matches all word characters from here, and for second token, it matches this colon. When we run it, we get this regex match. So when an attempt to match fails, regex engine looks for alternate ways to proceed and tries every possible way to match all tokens in regex to the characters in input string. Remember, starting character in every new line, that means in this second line also, it is preceded by a new line character and a carriage return, which are non-word characters. Hence, in this regex, if we take capital L here, after all possible attempts to match characters from the beginning of the string, regex engine restarts an attempt to match word characters from here for the first token. This plus is by default a greedy quantifier. It matches all word characters till before next carriage return at first. Now for matching second token capital L, Regex engine gives up one character from the end matched by the first token in search of capital L for the second token. It backtracks to first token many times and continues giving up characters until it can find capital L to match for the second token here. That means finally when we run it, it provides this regex match. If we take capital K as second token in regex here, run it, it matches possible longest sequence of word characters providing a capital K for second token in regex at the end. Notice that it matched so many capital K's here, then here another capital K before it matches this last capital K for the second token. Because plus is a greedy quantifier, it matches as many as possible. If we append a question mark to plus here, run it, now it matches as few characters as possible for all tokens in regex and provides this shortest match. Plus followed by question mark, we call it a lazy quantifier for matching one or more characters. And instead of question mark, if we append a plus here, run it, it matches nothing. Plus followed by plus, we call it possessive quantifier for matching one or more characters. This quantifier also greedily matches as many characters as possible like a greedy quantifier, but it restricts regex engine to give up any matched character when it needs to backtrack within regex tokens because it is possessive. As a result, it matches nothing here. It matches one or more word characters from beginning if we remove capital K from here. It matches nothing if we pass a word character like the capital K as second token here, because this possessive quantifier does not let it give up a word character while backtracking. But if we pass this non-word character colon here as the next token, run it, it matches this part from here. In this case, it does not need to give up a word character. Remove colon, and if we pass a token 4 here, run it, it starts matching word characters from here. Now here after this greedy quantifier plus for matching one or more word characters as first token, if we pass a capital J as second token, I'm just trying to get any match from here. Run it, it matches nothing, because this plus quantifier here tries to match at least one or more word characters, but there is no word character before this capital J here. In this situation we can pass asterisk or star in place of plus here to match 0 or more word characters. Run it, it matches this capital J here. If we pass has as second token in this regex, run it, it matches this part containing a has at the end. Now if we pass a dot, then this quantifier star for matching 0 or more times any character except new line as first token, then literal character has as second token. Run it, it gives this longest possible match. By default, star is also a greedy quantifier. It matches as many characters as possible. So here if we append this question mark to star, run it, it becomes a lazy quantifier and it provides this shortest possible match. If we append plus to star in this token here, it becomes a possessive quantifier. Run it, it provides nothing. If we pass a literal character equals sign here, then dot with 0 or more characters possessive quantifier, remove has. Run it, it gives this match now, because no character is given up in this case for matching a token in regex. We will see usage of another quantifier. Take dot, then plus quantifier for matching one or more characters as first token, then equals sign as second token. Run it, it matches here. If we pass a question mark in place of plus here, It is a quantifier to match 0 or 1 character. It matched only 1 character before equals sign here. If we attach it for matching 0 or 1 word character, run it. It provides only equals sign by matching 0 character before it because equals sign is not preceded by any word character here. Similarly, if we pass at instead of equals sign here, it matches only at sign here as it is not preceded by any word character. But if we permit 0 or 1 any character except new line character here, it matches equals sign before at. This quantifier is also a greedy quantifier. If we pass equals sign here as second token, it gives longest possible match 2 equals sign here. If we append a question mark to it, it becomes a lazy quantifier and it gives shortest possible match only 1 equals sign. And if we append plus to it, it becomes a possessive quantifier. It gives 2 equals sign again as the regex match. Quantifiers are all greedy by default. In specific cases, we need to use lazy and possessive quantifiers. Usage of few more quantifiers we will see later. Let's take this regex only a literal character, capital H, run it. It provides this earliest match, capital H here in search file at position index 45 in the string str fetched from this file. We pass one more character A, run it. It finds the earliest match here, capital H, A. If we write these characters within parentheses as a group, run it. It captures matches group-wise from the search file. This regex has one group. Here it provides this match capturing this pattern in the first group of regex. If we write A capital H here, run it. It could not find a match for this pattern in the group. But if we write A or H in this group, run it. It captures this A in the group. If we take two groups, one is capital H A, another is R R, run it. It captures group-wise matches in the regex match. Now while capturing groups, we can get captures field in regex match M. Pass it to println function. And for each matched group, we can get position indices where it matched in the string by checking offsets field. Run it. These are the captures and these are the respective offsets of the captures. If we pass this group R Y here, it matches nothing. Although if we pass this group Y or R, it captures group-wise matches in regex match. In this regex, let's pass another group to capture Y space capital P. Run it. It matches nothing because capital H A R then another R here, which is not being captured by any group in the regex. So if we allow this group to capture R also, run it. It matches here. If we pass another group to capture here, capital P A, run it. Obviously, it matches nothing because there is no capital P A here. In this situation, we can attach a quantifier for matching this group 0 times or only once. Run it. Now it worked, showing it captured nothing from the third group. Here we can notice by default it assigns groups to numbers. If we want, we can assign these groups to individual names. To do so, inside this group, write question mark, then within angle brackets pass group name, group 1. Then here also similar way pass group name group 2. Then here pass group name group 3. Then here pass group name group 4. Run it. And we see these groups are renamed. I should mention about another field match of regex match object M. It provides only the matched part of the string here. Run it. Here it is. So far you might have noticed we actually allowed regex engine to find earliest matches for the possible regex patterns in the search file. Now we want to get not only the earliest match for a regex, we want to get all possible regex matches and their locations in this entire search file. For that purpose, we can use each match function. Pass pattern, pass string str. It provides an iterator from which we can create an array containing all regex matches. Assign it to a variable matches. To find locations of all regex matches, we can call findAll function. Assign it to a variable locs for locations. Then we can use a for loop for I in the range 1 to length of locations. Print as respective tuples with its first element location of the ith regex match. Second element in ith regex match, the match field. End this for block. Run this whole Julia script. Here we get all matches from search file with their respective locations as ranges of indices in the string str fetched from it. We get these 4 matches within 4 ranges of indices. Many times regex matches overlap on each other in the input string. As example, let's take this class of characters equal at hash. Run it. It gives all these matches of any of these characters in search file and their respective locations. Now if we want to match sequence of 3 characters, each of which is either of these characters, run it. We get these matches here and here. Instead of writing this character class 3 times, we can attach this quantifier within curly brackets 3 also. Run it. We get same matches. These matches and locations of these regex matches are disjoint or separate to each other. Now if we want to allow this regex engine to consider matches overlapped on each other also, we can pass here and here this keyword argument overlap equals to true. Run it. We get these matches. Here somewhere in middle of this search file, we can find few movie names. Suppose we want to match only the movie names which start with Titan. So in regex, if we pass this pattern Titan, run it, we get these 2 matches, but not any movie name exactly. Pass this character class to match either S or I or C at the end. Run it. It matched the first movie name Titans, but it could not match the second movie name. Attach plus quantifier here for matching characters 1 or more times from this character class. Run it. It matches 2 movie names, but not the third one. One reason not to match anything from this third movie name is it starts with capital T. We can make this regex case insensitive. Outside the double quotes, append this flag I here. Run it. It matched part of the third movie name. Include A in this character class. Run it. Now it matched the third movie name also. In search file we have these book names. Some of these are Harry Potter books and some are Sherlock Holmes books. We want to match these book names using regular expressions. At first, let's simply try to match this pattern. Harry. Run it. We get these 4 matches matching Harry only. Let's try to capture patterns group-wise. Harry or Sherlock. Run it. We get all these matches matching to Harry and Sherlock as well. Now we need to match entire book names, each of which includes Harry or Sherlock. So we need to capture the characters followed by or preceded by the pattern Harry or Sherlock. That means we can pass dot with star quantifier for matching 0 or more characters except new line character before and after Harry or Sherlock. Run it. We get these book names, but these are all trailed by a carriage return here. That's why we need to pass this metacharacter \S for negating any trailing carriage return to match. Run it. Here these are. We can make this output in REPL look better. Inside this tuple, assign these respective ranges of indices of the matches to a variable span and these matches to another variable match. Keep it within parentheses. Run it. It provides these named tuples containing the matches and respective spans, that is, the ranges of indices in which the matches took place. Now we want to match all these dollar amounts. These are respective prices of these books. So at first, let's pass this dollar sign here in Regex. Remember, we need to escape this dollar here to let Regex engine consider it as a literal character. Otherwise, it will be taken as a metacharacter. In price amount, dollar is followed by one or more digits here. So we can pass this character class 0 through 9, from which one or more digits will be matched. Run it. Here these are. We are not done yet. These matches should be trailed by decimal point, followed by respective decimal parts, if there exist. Keep this part in Regex within parentheses as a group to capture. Inside this group, start another group that includes a decimal point followed by one or more digits. Run it. But it could not match this $11. A price can be without decimal point and decimal part also. That's why I append this quantifier question mark to this group for matching this group never or once. Run it. We get all the dollar prices matched. I should mention, in place of class of digits here and here, we can simply write this metacharacter \d. Run it. Okay, next is we are going to match these dates or months of publications of these books. At first, let's try to match these years. Each of these years starts with 18 or 19 or 20. So inside a group, 18 or 19 or 20, followed by 2 digits. Run it. We get these years matched. 1 comes twice here. So we can write this way also. 1 followed by this group 8 or 9. Run it. These years are preceded by a literal hyphen. Literal hyphen is preceded by one or more letters. These letters are preceded by a capital letter. Capital letter is preceded by hyphen. Hyphen is preceded by minimum 1, maximum 2 digits. Run it. We get these matches. But here in this date, these are spaces, not hyphens. That's why we can pass here and here a character class of hyphen and space. Run it. Now it matched this date also. Now instead of dates, here we have few publication months also. To match this format also, we can take this part as a group. Attach this quantifier to this group to match it 0 or 1 time. Run it. We get all these publication dates and months as well. In search file, these are few imaginary names. Each of these names starts with a specific salutation. Capital MR dot, capital MS, capital DR dot, capital PROF dot, here capital PROF, then capital MRS dot. We want to match all these full names. So at first in Regex, take a group of all these salutations, capital MR dot or capital MRS dot or capital MS or capital PROF dot or capital PROF or capital DR dot. Run it. We get only these salutations. Here we can use smaller group also. Capital M followed by this group R dot or rs dot or s, and here capital PROF is followed by 0 or 1 dot. Each of these salutations is followed by one or more characters. Run it. We get all these full names matched, but each of these matches is trailed by a carriage return. So pass this metacharacter \S for negating the trailing carriage return to be matched. Run it. Here these are. These names are followed by respective contact details, email IDs and phone numbers. At first, let's match these phone numbers. Each phone number here starts with a sequence of 4 digits, then space, then sequence of 3 digits, then space, then sequence of 3 digits. So we can create this regex here this way, \t to match exactly 4 digits, followed by space, then \t to match exactly 3 digits, followed by space, then \t to match exactly 3 digits. Run it, and we get all these phone numbers matched. We will match these email IDs now. An email ID always contains this @ sign, which separates this local part and this domain part. If we take this @ sign in regex and if we pass \S with plus quantifier for matching one or more non-white space characters before and after @ sign, run it, it matches all this. But this is not an email ID, and here this also cannot be an email ID, because in local part it cannot have any new line character, it cannot have another @ sign. In domain part it cannot have underscore, so we need to be more specific. For local part, pass this character class, letters A through Z, digits 0 through 9, underscore, and all these printable literal characters except @ sign. Attach plus quantifier to match one or more characters from this character class. In domain part, there is always a literal dot which can be preceded by one or more characters from A through Z, 0 through 9, and hyphen, except any underscore, and can be followed by one or more characters from A through Z, 0 through 9, hyphen, and literal dot. Run it, we get all these matches, but it could not match this email ID properly containing capital letters. Email IDs are not case sensitive. Here we need to append this flag I to make this regex case insensitive. Run it, and we get all these email IDs. If you want, you can pass this word boundary at the beginning and at the end. Run it. In place of these letters, digits and underscore, we can pass this metacharacter \W as well. Run it. These are some time lengths here in search file. We need to match these time lengths. If we write this regex this way, for hour part, one or more digits, colon, for minute part, one or more digits, colon, for second part, one or more digits, run it, we get all these matches. But this is not a valid format of time length. This is also not a valid format of time length. As a time length, we can let this hour part be any small value or large value or just 0. But this minute part and this second part cannot be greater than 59. So we can write here for hour part, one or more digits. For minute part, first digit can be any digit in 0 through 5. Second digit can be any digit in 0 through 9. For second part, first digit can be any digit in 0 through 5. Second digit can be any digit in 0 through 9. Run it. We get all these time lengths in valid format. Of course, in place of this character class 0 through 9, we can write this metacharacter \d also. Run it, we get the same time lengths. We are going to match valid IP addresses from here now. An IP address, specifically a version 4 IP address, consists of 4 numbers separated by dot. Each of these numbers ranges from 0 to 255. So to match these numbers in this format, we can write the regex in this way. 4 groups of digits to capture, which are separated by 3 literal dots here, here, and here. Suppose first group starts with either 0 or 1, which can occur or not as well. Next character can be any digit. Next character also can be any digit. But this group can contain only one digit also, the middle digit. Thinking about that possibility, attach this quantifier for matching this digit 0 times or once. Or this group can start with 2. In that case, we need to remember that number captured by this group cannot exceed 255. That's why next character can be any digit in 0 through 4. Next character can be any digit. Or this group can start with 2, next digit can be 5, and next digit can be any digit in 0 through 5. This same syntax we can apply for next 3 groups also. So copy this, then paste here, here, and here. Run it, we get all these matched patterns. But it captured this pattern which it took from here, not the whole pattern. To restrict it to do so, we can pass a word boundary at the beginning and at the end here in regex. Run it. So out of these 8 patterns in search file, it captured 5 patterns as valid IP addresses we see in REPL. Now let's match these web addresses or URLs. Each of these web addresses starts with either https:// or http://, which is followed by one or more word characters before a dot. So we can write this regular expression as https:// followed by one or more word characters followed by literal dot. Run it. It matched only these parts of the website addresses. We get only all these https here. So we need to attach this quantifier to match 0 or 1s. Run it. Now it included patterns with http also. Then let it match any character at least 2 or more times. Run it. We get these matches. But it matched this address, which are not valid because a web address cannot have underscore in it. To stop it to match pattern which contains underscore in it, we can do negative look ahead for underscore, as we see in this list of metacharacters here. So here in regex, before literal dot, negative look ahead for underscore, and after literal dot, negative look ahead for underscore. Run it. Now we face another problem. It matched this address incompletely. In this situation, we can make regex engine to consider beginning and end of string for every line. To do so, we need to append this flag m here so that it treats the string str fetched from search file as multiple lines. Now run it. We get these web addresses matched, but each match is trailed by a carriage return. Because every line ends with a carriage return and a new line character here, as we see in raw format of string str. If we print these matches only, remove this name and this part also, run it, we can see Julia prints these valid web addresses properly without any trailing carriage return, because carriage return and new line characters are not printable characters. But the way we have been getting these matches together with the ranges of indices they exist in, if we want to get these web addresses in this same way, just to get rid of these carriage returns, we can replace these carriage returns by empty string, and we need to correct these ranges of indices also. Because as example, this pattern till before carriage return exists in the range 1621 to 1667, not 1668. That's why in this tuple we can write this way: span equals to range ith location first index to ith location n index minus 1, and match equals to pass it to replace function with dot syntax. For broadcasting, we are going to replace carriage return by empty string. Run it, and we get these valid web addresses with respective ranges of indices in which all these exist. Thank you for watching. Hope you found this video informative. For any query, please write in comment section below. If you would like to support, simply click on thumbs up button, share this video to someone who may find it helpful. You can subscribe to this channel as well. See you in any other video. Goodbye and have a good day.